So for the next bit of time, like weeks, we're going to do a lot of random walks, stuff related to random walks. This is the first one, okay? Random walks are very interesting, but one thing that will change is that there's going to be a little bit more linear algebra, okay? Because it turns out that random walks are often well understood from a linear algebraic perspective. And part of the reason why I teach this is to force you guys to learn a little bit of linear algebra. Yeah. Will we be looking at the algorithm for estimating volumes? Probably not, but it's in the ballpark. It just very analytical. I could, but there's yeah trade-offs. Um, but we'll certainly be in the neighborhood of this. Yeah, later you can tell me why you're interested. But anyway, oh, you heard about it once. Yeah. Um, uh, So random walks are very interesting. It's also going to force us to learn a little bit of linear algebra along the way, which if you had a bad experience with linear algebra before, I think this will actually be much more fun because it's really about the structure inherent in linear algebra, which maybe some of you already work on with your research. But if you're just coming from like your typical undergrad linear algorithms class where like they made you do Gaussian elimination over and over and over again, you might not realize like how much symmetry and how much structure, right? You can get from analyzing linear systems as well. So everything we do will be in terms of graph, but there will be some interplay where we go back and forth between graphs and in linear algebra, and that should give you a slightly more qualitative understanding of linear systems, like something that actually like makes sense and is not just like what I'm saying is that matrices are more than arbitrary arrays of numbers. Like graphs make sense to us, right? We look at a graph, they make some intuitive sense to us. If you look at a grid of numbers, it's not clear what it means, right? Because we typically don't take as much of a structural perspective on it or geometric perspective on it. But so that'll also come up in this class, and that's one of the side goals of these topics. But anyway, so right, right. This is what we'll do. Okay, so this is I guess a map of the internet. Is it too small to see? Um, okay, so part of the internet, at least centered around the main page of Wikipedia, and I think also a long time ago, and stuff like this. I mean, I just got this from a Wikipedia article. But these are just like links and stuff, right? So a really big revelation uh, was when we started studying the link structure of the internet. Okay, so the earliest search engines were just doing like regex. They were just trying to match words. Okay, so if you wanted like a really good search result for university, you make a web page that goes university, 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 and uh, and if you don't want your web page to look bad, you just put in the comments, right? So uh, but then, some clever people inspired by, librarians and stuff who were always keeping track of citation counts and things like this said, oh, okay, the citation, if I interpret links as citations, the link structure, thinking about it as a graph, actually gives me a clue as to which web pages are better than others. And of course, that leads to everything until this past year. Um, where now, yeah, we'll see what ChatGPT does to this perspective. Anyway, so given a search query, right? The first thing you want to do is like, okay, what are some of the relevant web pages? So here you might, do your feature extraction. You might, you know, do some embedding and compare the embeddings. See what pages are kind of similar in terms of just content on web page compared to content of the query. Okay. But the second question is that, okay, among the reasonably well matching web pages, what are the most relevant ones to your query and what are the best ones? And that's the question we're going to focus on today. Okay. So this is a ranking question. right? And we're going to try to do something based on the structure of the web. So, it's just fun to think about. What are some ideas for trying to distinguish one web page from another? The degree. To say, okay, good web pages, they're directed graphs. So in degree or out degree? In. So a good web page should have lots of other things linking to it. Okay, that's good. Any other ideas? That's actually going to end up being the next slide, but any other ideas just for fun? Yeah, okay. We're going to talk about PageRank, but do you know what PageRank is? Well, okay. Let me just walk through this and, just pretend that you're learning something. Okay. So, first score is okay in degree, right? How many web pages are pointing to me? Okay. That's a natural first thing. Now, how do you break this? Yeah, you just create a bunch of web pages that just point to you, right? So, or as a researcher, I can just write a bunch of junk papers pointing to my own papers, right? And that'll get my citation count up. Yeah, I mean, there's obviously a lot that goes into it, but naively, you first gather up the web pages that have your word, and now you have to figure out how you're going to rank them. So we're looking at kind of the ranking question at this point. Yeah, you can use LSH, for example, as a great way to, yeah, but you might do it with respect to the embeddings instead of, where you first feed it through an LLM or something. But then you'll probably use LSH to try to find a near neighbor, right? You want to find something that's similar to your search query. Yeah, realistically, that's what I would do. Yeah. And another question also is another thing that's also asymmetric is that one web page has tons of links to the outside world has much more influence than a web page with a few. So imagine, okay, you're trying to find a good restaurant, and you have two lists. One list is called top 10 restaurants in the West Lafayette area. The other list is called top 10,000 restaurants in the Lafayette West Lafayette area. And someone says, "Oh, I found this restaurant on the top 10,000 list." And you're going to be like, "I didn't even know there was 10,000 restaurants," right? Like, obviously you'd rather be on the top 10 list. So another thing is that maybe we should scale things or something so that each web page can only contribute 1 point. So that's the second idea. Um, this is like in degree, but it's dividing out. Um, yeah. So at least each web page can only put out one total point. But now the next issue is actually the issue we previously mentioned is that now you can just make up a bunch of websites. Instead of having a top 10,000 list, you can make 1,000 top 10 lists, spread your 10,000 uniformly, right? You'll have the same effect as before, roughly. Okay. So, so these are two natural ideas. I'm sure they actually tried this. Okay. So how can I resolve this? Yeah. Yeah. Oh, okay. So maybe, yeah, so that's what we want to do. Yeah, yeah, okay, okay. So these fake websites shouldn't have other things pointing to it, right? As we know, there's not a finite set of fake websites. I think it's actually like Unclear if it's countable. I mean, it must be countable because it's bits somewhere. But like now that we have machines that it can make websites really, really fast. Um, okay, let me take this slightly different perspective. If I could weigh you by its own, I'm trying to come up with authorities, and I'm trying to define authority, value or ranking or authority of a web page, and I'm considering the authority bestowed by other websites. If I could use this own value of authority in a recursive way, then we might reach some kind of special nirvana. Okay. So if, let's look at this one, score three. Score three is defined recursively. So the third version of score for V is summing over all of its in neighbors, the score for that in neighbor divided by the out degree of the neighbor. So the neighbor can only still put out a certain amount. It can't just have tons of links and give out more points. Okay. But this seems like at some level sort of like a nice equilibrium. If you have a good ranking, it gives a good ranking kind of thing. It seems self-consistent. Okay. So you don't care if bad web pages are linking somewhere because you're hoping that bad has already been identified. Okay. Yes. Okay. So as appealing as this model is, don't worry about the faculty meeting. As appealing as this model is, it's not clear that these values exist, right? Like it would be nice to have, but it's not obvious that these values exist. Okay. So that will be the first theorem that we will do a full proof of. Okay. So, okay, stop this. Okay, so I guess we're going to assume that everything is normalized to add up to 1. Okay. In that case, here's our theorem. We can find, so delta to the V is like distributions over V, right? So I'm assigning values to every website. They sum up to 1. They're all non-negative. The claim is that I can find these non-negative scores so that this is true. Always, no matter the graph. Okay. Moreover, if the graph is strongly connected, then X is both unique and strictly positive. Everything has positive value. Yeah. You can go from A to B and from B to A. Yeah. So, yeah. So that's the first theorem that we're going to try to prove. Okay, so this is very nice because it works for all graphs. Okay, but the question is why? Um, yeah, but there's some ways to fix this. So, but I'll explain a little bit later when it makes more sense. Okay. Okay, so the reason why has to do with trying to interpret things in terms of a random walk. Okay. So random walk means you're at a vertex U and you choose one of the outgoing edges uniformly at random. You can add weights to the edges, in which case you pick a edge in proportion to the weight. Okay, but you're just randomly walking around through a graph. That's of course well defined for any graph. Okay. So let's see what's here. After taking 10 steps from, say, some particular starting vertex, or you can start from like a uniform distribution over all the vertices, there's some distribution of where you're going to be after 10 steps, right? And the question is, will this distribution converge as k goes to infinity? Um, right, right. Is the answer always yes? Yeah, what's an example of a graph? Yeah, or even just two vertices. Back and forth, back and forth, back and forth. We'll have very distribution for k is even, k is odd. So we'll have to rule that out somehow. Okay. Now, so a stationary distribution is when something converges. Okay. So here's a simple graph. What is the stationary distribution on this graph? Uniform. If you put 1/3 everywhere, you take one step and the 1/3 just spins around the triangle. Okay. So somebody's outside the door for some reason. Okay, so here's our how we're going to restate our theorem. Okay, is that the stationary distribution means I'm at the stationary distribution, I take a random step, and I'm still at the stationary distribution. Now, 1 divided by out degree I can think of as the probabilities assigned from the random walk. So I'm here, and I choose one of the neighbors uniformly at random, and I go there. So when we say that the score of V is equal to, the sum of U, the score of U divided by the out degree, we're really asking for is whether there's a stationary distribution. Okay. So we're saying that G is every random walk is a stationary distribution. If G is strongly connected, somehow I should rule out bipartite graphs. It's not included here. Distribution is unique. Okay. This is not obvious. Okay. Remember, this is a directed graph, right? So that matrix is not a symmetric matrix. Okay, so you're not promised like a nice real valued eigenvector. Yeah. So I'm missing some qualifier here. Yeah. It's not a perfect theorem. Well, okay, if you're the web crawler, you can just ignore the links to itself. Okay. Okay, so next time we'll try to prove this, and we're going to learn a little about linear algebra on the way. Maybe I'll address this one question. What actual random walk would you actually do if you're a search engine in 1998? Do you know what they did? So they would start the random walk at a reliable web page like yahoo.com, which actually hired people to try to like make basically a phone book out of the internet. Okay, like, oh, what are the best sports websites, this and that. They would start the random walk there, walk around. Each step was probability, 1 in 100. You restart at Yahoo. So you stay pretty close, or you can choose some newspaper that you like or something like this, right? So you start with an authority, you kind of put extra emphasis, say, I trust this, and you have the random walk restart from time to time. So if some weird part of the website tried to make some really well-connected part of the graph that a random walk can't escape and things like this, well, you're always going to be able to restart back to Yahoo, and you're going to generally be in the vicinity of yahoo.com. Okay, so that's the actual page rank, is that they looked at, for a fixed sort of initial distribution, they would restart the walk every once in a while. And the initial distribution would be some curated set, okay, of reliable websites. Yeah. Yeah. I mean, that was, initially Google would only update once every 3 months or something. It would be like a news news item, like, oh, Google updated their thing, and now they can do it quietly all the time. Yeah, but if you read kind of like I am reading one now, kind of early books about Google, this was quite painful. Internet was a little smaller back then, and also they weren't like people weren't trying to game the system quite as much back then. Um, People didn't really even think that this was like a reasonable thing to do to try to, download the entire internet, but they just went ahead and did it. But they wouldn't even save the web pages, just save the link structure because that's what they needed for the page rank. And they might save some keywords for the matching. Yeah. And then they added more features over time. But that was the initial thing that really set them apart and was the first time you got like fairly reasonably good results. Yeah. Other questions? That's it for today as far as technical stuff goes. Okay. Have a nice weekend. Okay, so we started discussing this on Friday, so I'll get us up to speed. But the story is, right? Imagine you're making a search engine in 1995. When did these guys start? 95, 90, 95, 96? Anyway, first you have to figure out the relevant web pages. Maybe back then you're just looking for keywords. These days you're going to do some vector matching, LSH over the embeddings. But then you want to find the most relevant or kind of the best web pages among the ones with some superficial match. And that's the question we're interested in. It's a ranking question. And, the big insight was, okay, let's try to actually use the structure of the web, not just look at the websites, but look at the links between the websites. And believe it or not, that was a novel idea in this space. Okay, before it was just like a big grep over the internet. Now they're actually going to look and think about it as a graph. And we discussed some ideas. One question is like, okay, why don't I assign a score, which is just how many edges point to me? Okay. But for example, if you do that, then one web page can give out 1,000,000 links and sort of have a lot of influence. So, imagine you have two websites. One website says top 10 restaurants in West Lafayette. The other website says top 1,000 restaurants in West Lafayette, which I don't know how you don't make that list because I don't think there's 1,000 restaurants in West Lafayette. Obviously you'd rather be on the top 10 list. And so that's sort of silly. So one second idea is, okay, let me divide by the number of out degree for a website. So that top 10 list is giving 1/10 of a point to each restaurant because it made the top 10. The top 1,000 list is giving out 1/1000th of a point. Okay? Like, okay, that's a little bit better. But now I can just take a top 10 website and just duplicate it 1,000,000,000 times, right? And just keep increasing the score. Okay? So at some level now it's like, okay, what gives these top 10 websites the authority to bestow certain points, right? And it's like, okay, well, I'm trying to come up with some sense of goodness, and maybe I want to use goodness of the incoming links to sort of moderate that. So you come up with this recursive approach. Okay, so you're assigning a score to every vertex, which is going to be the sum over all other incoming edges, the score of that vertex divided by the out degree. Okay, this seems nice. There's something kind of self-consistent about it, right? If the scores are stable, then it's kind of, yeah. So there's a nice nirvana here, but the basic question is, why would there be anything that satisfies this system of equations? Okay. Now, right, so that's the question that we're going to answer today, right? Sure. So you're assigning some kind of point system to the vertices, right? Because you're trying to score things, and so higher the better. You want points. So you're looking at the incoming vertex. It's a top 10 list by a highly reputable source or something, and say, okay, I'm going to count that top 10 list for more, and then here's a top 10 list from a very dubious source that no one believes in. I'm going to give that a low score. It's not going to affect anything either. Okay, how do I figure out which of the incoming websites have more authority? Oh, I'll just use the system I'm developing at the same time. Right? So it's the modeling that's the interesting thing, but it's not true that it's not obvious that this exists. Okay, something that satisfies these values. So that's really what our goal is to prove today, is to prove that you can find such values X. But it has also nicer properties. It's going to be positive with non-negative values, okay? Which means you can rescale it to sum up to 1. So you could think of it as a distribution. In fact, if G is strongly connected, it's going to be both unique and strictly positive. Okay? Yeah. The graph is strongly connected in the way we often talk. So that means that A can go to B and B can go to A for any choice of A and B. It's a directed graph, so. That's from graph algorithms. That's like if you remember taking like strongly connected components in maybe an undergraduate algorithms class or something like this is sort of in that chapter. Yeah. Um, yeah. Okay, so good. And the reason has to do with the fact that you are actually modeling a random walk. Yeah. Uh, right. So I guess the point is that there's a non-zero solution, a non-trivial solution, because if you put zero everywhere, yeah. So this theorem just says for this particular system of equations, right? I'm just trying to fill in for score. There is a non-zero solution. So if I just write, arbitrary systems of equations, there could be contradictions between them and stuff, right? Not all systems of equations have solutions. That's why we have things like regression where we minimize sum of squared error because we don't have an exact answer. But what we're saying is that this particular thing that sort of came up in our discussion, trying to come up with a reasonable way to rank websites, does always have a solution that's non-zero, it's non-trivial, and has additional properties. Every entry is positive if the graph is connected. Okay. If the graph wasn't strongly connected, then all the entries would still be non-negative. Okay. And now that all the entries are positive, I can always rescale any solution because it's just a linear system. So that means I can rescale sort of probabilities that all the entries sum to 1. So you can interpret it as a probability distribution. Yeah. Well, it forces at least one thing to be non-zero. Yeah, yes. Yeah. Yeah, I didn't have to write non-zero x in the simplex. So that's the kind. But the real thing is like, you shouldn't take for granted there is a solution to a system of equations. It's actually very delicate as to why this even exists. And that's what we're going to try to focus on today. And I'm going to use this also as an excuse to force feed some linear algebra background. Yeah, every entry is positive. That's right. That's right. When it's strongly connected. If it's not strongly connected, then you could have zeros and stuff like this. Yeah. Okay. So, good. So the reason, and we'll explain why mathematically, but the high level reason is because this system that we came up with for scoring websites can also be interpreted as a random walk, right? So, and a random walk on a graph means you're at a vertex, you choose one outgoing edge uniformly at random, you keep walking around, okay? And if we look at our system, so this is the one we did together, but as you do a random walk for long enough, right, the probability mass keeps spreading. So if you're here and you have two choices, then you have probably one half. So And gradually probability kind of diffuses. Does it actually converge to anything? That's a question. But if it does converge, it's called a stationary distribution. So this is some distribution over the vertices. You could be here 1/10 at a time, there 1/10 at a time. And if you took that distribution and you simulated one step of the walk, sorry. So, I jump to a vertex with the probability given in distribution, and I take a random step, and then what are the odds that I'm at various other vertices? You'll recover the same distribution. So it's like kind of fully mixed, right? It's an equilibrium, okay? So that, this one here, if I could be at any of those vertices, probably 1/3, and I take one step where there's only one edge I can follow, then you'll end up with 1/3 for each vertex afterwards. Yeah. Good. So, that system that we came up with just to try to rank web pages is also describing a random walk. So if I'm at a vertex with probability xv, and I choose one outgoing vertex uniformly at random, then I'm going to take my probability mass and distribute it evenly. So divide it by the out degree. Okay. So when I write xv is equal to the sum over all edges going into v, xu divided by the out degree of u, that's okay. I'm xv, and at the stationary distribution, how much probability mass comes to me, it should be as much as I currently have. So every random walk has a stationary distribution, and if G is strongly connected, the distribution is unique. I guess it should also be strong positive too. I forgot that. Okay, now the question for this is why. Okay. So, some basic linear algebra stuff. What does it mean for a function to be a linear function? Yeah. Yeah. Okay. So linear functions like this. Okay, you've probably all seen this before, right? And I think maybe the spectacular thing about, so first of all, this is the easiest function you can ask for, right? If you had like less options than this, what else can you do? Now, the spectacular thing about linear algebra is that in fact, linear functions have a lot of structure. And today will be one such example, and we'll explore this as a theme for the next couple of weeks. So, okay, all linear functions have the form. So, there's n output coordinates. If I'm looking at the ith output coordinate, it's going to be of the form summing over j, ai, j, xj for some unique, n by n arrangement of numbers, also called a matrix. I guess we've seen matrices before, so that's not too okay, we've seen linear functions before. I forgot about Johnson-Lindenstrauss. Okay, so a graph, for example, can be thought of as a linear function, okay, where I have some inputs on the vertices, and I just send them across every single edge. Okay, so it's actually going to be a transpose, so to speak, of the adjacency matrix you sometimes see in class. Yeah, so I'm just putting a 1 if you can go from u to v. AVU is equal to 1 if you can go from u to v, only because I'm thinking of AX as going from to another. Okay. So for example, score number 1 in terms of A, okay, is summing up over all the edges coming in 1 point. So that could be written as A1 sub V, where 1s is the all 1 vector. Okay. I mean, nothing interesting. This is just notation. The out degree of a vertex U, well, that would be, I could apply, let's see if this makes sense. So E sub U will be the vector that has a 1 on coordinate U and 0 everywhere else. Okay, I don't know, is that bad notation because we have edges? Okay, we can always change notation later. Uh, so this vector here will have a 1 for every vertex v where I can go from u to v, and a 0 everywhere else. So if I want to sum all that together, I'll take the dot product with the all ones vector. Okay, so these are just simple examples. Okay, yeah? Yeah. So it's like the opposite of what we sometimes call an adjacency matrix in the regular algorithms class. Yeah. Okay. Um, okay. So the random walk matrix. So if I let D be the diagonal matrix with all the degrees along the diagonal, D inverse is also like putting 1 over the degrees on all the diagonal. Okay. So in a random walk, I'm at a vertex U, and if I have degree 10, I'm going to divide by 10 and send 1/10 of my value across every edge. Okay. So that's going to look like AD minus 1. You can verify this in case that explanation wasn't good enough. So like if I want to check two coordinates, right? Uh, what's the point of this? Well, anyway, this is probably what we think of as the random walk we modeled, right? 1. And this is the probability mass that's sent from U to V if U had 1 unit on it. So just verifying calculations. I always remind myself nobody wants to watch me do linear algebra all day. So score 2, right, where we divide it out by out degree, would in linear algebraic terms be just applying the random matrix to the all ones vector. Okay. And is there anything else here? Okay, the stationary distribution is some x such that x is equal to Rx. Again, this is just notation, no new content, it's just notation. Okay, and that's what we're looking for score 3. Okay, so what's it called when x is equal to Rx? Yeah, that's true, when it's non-zero. So whenever you have something of the form ax is equal to lambda x, where I guess I should have wrote that x is non-zero, lambda is some scalar, okay? That's called an eigenvalue, an eigenvector, right? Which means like, because A itself is like a very complicated big mess of numbers, right? You look at stare at A, you're like, what the hell is this? But an eigenvector is a direction where A is actually very clear how it works. In this direction, it just stretches things out. It doesn't rotate anything. Okay? Otherwise, A can be a big mess. Okay? So eigenvectors are particularly nice. There's no reason why they should exist. Okay. So in this language, again, it's the same theorem. If G is a directed graph and R is a random walk matrix or linear map, then you do always have an eigenvector that is a distribution that gives you a distribution over the vertices with eigenvalue 1. Okay, and it's unique and it's strictly positive if G is greater than 0. Okay, so what started as a page ranking problem has turned into sort of a classical statement about random walks. Right? This is the kind of thing that, I don't know, 150 years old, 200 years old? I just assumed Gauss knew this. Okay. What didn't he know? Well, I mean, other people came along. Einstein came along. Okay. They have his notes. Um, okay. So this is not obvious. Every linear map has an eigenvalue lambda and an eigenvector x. I know you've probably been exposed to this before, but it's not obvious. Okay. Not only that, but it's not even quite what we want. What's the biggest defect of this lemma? and it's complex. Oh, yeah. Assume like just put non-zero whenever that's but it's complex, right? We're actually not even guaranteed a real eigenvalue, real eigenvector. What the hell are you going to do with a complex web page score? It's like, oh, okay, this web page is 2 plus 3i. Great. Like, you know. So so this is actually not where we want to end up, but is still a starting point, right? The existence of eigenvectors. Okay. Anyone remember how to prove this? Okay. Yeah. Okay. So you know that a minus lambda I x is equal to 0. Okay. And then you just threw out the word polynomial, but what's the connection to the polynomial? Yeah. Okay, okay. So you want to say if you have an eigenvector with eigenvalue lambda, then you must have that a minus lambda I. So you're looking for lambdas where a minus lambda I is not invertible, which means what? Okay. Okay. So if you look at the determinant of a minus lambda I and you write out the whole thing, okay, there's an easier proof. Anyone want to do an easier proof? Because I don't want to write out anything to do with the determinant. So x, so in general for a polynomial b, x equals 0 does not, it's not a symmetric matrix. Uh, yeah, okay, but then you'll get some value lambda, so that xa minus lambda I x is equal to 0. So you'll end up with a lambda such that, oh, so if you wrote x a minus lambda I x and you expand that out to some kind of polynomial of the xi's and xj's, okay? Every polynomial over Rn will have. So this has n variables, not one variable. So this is going to give me some sum of the form, uh, beta ij xi xj, where the betas might include some lambdas in it. Okay. Okay, between can you just and somehow. Okay, here's a proof that's not going to, yeah. Uh-huh. But then you have to start doing this, worrying about this for symmetric matrices. Yeah. Yeah, what are we applying the fundamental theorem of algebra to? Yeah. Okay. So the characterist polynomial, that's the determinant approach. Okay, here's a different approach. The determinant approach will work, but I hate the determinant. So, uh, okay. Oh, it's not here. It's here. Okay. So, all right, take any non-zero vector v. We will use the fundamental theorem of algebra. Okay. And look at these vectors. V, AV, A squared V, A cubed V. I keep going. A minus NV, A N V. Okay, that's a start. Okay, how many vectors are there? N plus 1? Whoa. Okay, let's undo that. Okay, there's n plus 1 vectors. Okay, what does that imply? There's some linear dependency, right? So there's some linear dependency. What does that mean? That means you could find some polynomials, some coefficients. Alpha 0 v plus alpha 1 a v, alpha n v is 0. Okay, where not all the alphas are 0. Okay. Um, okay, so that means that if I think of those alphas as the coefficients of a polynomial, there's some polynomial out there such that PAV is equal to 0 and the polynomial has degree n. Okay? Okay, what do I do next? So if I apply the fundamental theorem, then I know that P of x has this form. For n complex roots, they might repeat. All right, fundamental theorem of algebra. Now what? Those are not all your eigenvalues. We're just trying to show there exists one eigenvalue. So what's next? What's the next step? Okay, so since I know that, sorry, that should be 0. Since I know that PAV is equal to 0, the all zeros vector, whoa, I just wrote like all this random stuff. Okay. RNIV is equal to 0, right? I'm just plugging A back into the polynomial. Okay. So what does this imply, right? So either this term is, so at some point 0 appears, right? So either this term is 0, or the first two terms give you 0, or the first three terms give you 0, or the first four terms give you 0. So if it's like if it's the 10th term that gives you 0, that means the first 9 times v gave you something non-zero. And then the next term, it'll be the 10th r would be the eigenvalue. Okay. So as you keep applying this, at some point it becomes a 0 vector. Right when it becomes, that r is your eigenvalue. It's not an eigenvalue for v. It'll be the eigenvalue for the first 9 applied to v. Yeah, so P of A is all of this. And P was just generated from looking at the linear dependencies of these n+1 vectors. P of x is what? Oh, yeah. So for any polynomial, you can always interpret it as a polynomial of a matrix, which is what I did here. I mean, you can plug in a matrix for a polynomial and interpret it nicely. Not sure if I'm addressing the question. Yeah, just some value. All your promises is a complex value because that's what the fundamental theorem of algebra gets you. Oh, yeah, this is we're never saying that eigenvalues are never saying that a minus lambda I is zero, just saying a minus lambda I times some vector x goes to zero. So yeah, so this is the simplest proof I know of this because character polynomial always sounds complicated, right? So okay, good. So this is important, right? And I think the idea, okay, so this is just a statement about math, so it's some closed formal, hermetic system, and you just study the rules, and the rules give you something for free, right? And the fact that we're going to be able to map this and get something useful out of the real world, I think that's fantastic. Okay, so let's keep going. Now the issue is that it's complex, right? Okay, so, okay, we have to go a little quicker. Okay, so next thing, I think you all know what a transpose is. One definition is that transpose is a unique matrix A transpose such that x dot product AY is always equal to A transpose XY. Okay, for all x and y. That also means you rotate it, but I actually try not to think about literal grids of numbers when I think of matrices. So, okay. Okay, why is this necessary? Not sure. All right, quick thing. A is invertible if and only if A transpose is invertible. Okay. Why? Uh, okay, well, you can write X. So you might guess that if A was invertible, then, okay, so if you look at something like this, okay, and you just start flipping things over one by one, okay, this lecture is always a little weird because it's like, did we do anything besides flip things over? And the answer is, I'm not sure. Okay, so if X times this monster is always equal to X dot product Y for all X, then Y must be equal to that monster. Okay, which means that A inverse transposed is equal to the inverse of A transpose. Okay, fine. Um, A and A transpose have the same eigenvalues and the same multiplicities. What's the easiest way to do this? I guess it's actually not that interesting. Uh, you just write A minus lambda I transpose is equal to A transpose minus lambda I because I transpose is equal to I. So if A minus lambda I is, and what we just did before is A is invertible if and only if A transpose is invertible. So if A minus lambda I is not invertible because lambda is an eigenvalue, then A transpose minus lambda I is also not invertible, and lambda is an eigenvalue. Okay, fine. I can tell you're all super excited. All right, here's the thing that actually matters. Okay, this is called the Perron-Frobenius theorem. Okay, remember, you only promised in general that there's some complex eigenvalue, complex eigenvector. Okay, somewhere around here, we need to say, oh, there's a really nice eigenvector where everything's strictly positive and eigenvalue is 1 and all these things. Okay. So first, start at the top definition. I should have hit everything first. I'll say a matrix A is positive if for any non-zero choices of x and y, x dot product ay is strictly bigger than 0. That means all the entries are greater than 0. Okay. So, Perron-Frobenius theorem says if A is positive, all the entries are positive, then A always has some eigenvector and some eigenvalue such that we already knew. The interesting is what you're promised. Lambda 1 is strictly greater than 0, and the eigenvector is coordinate-wise greater than 0. Okay, so that's special. x1 is the unique eigenvector of lambda 1. X1 is a unique non-negative vector such that ax1 is greater than or equal to lambda 1. All other eigenvalues have strictly smaller absolute value. No other eigenvectors are non-negative. Okay? So just because the entries are positive, you're getting a crap ton of structure about at least one of the eigenvectors. Actually, many of the eigenvectors, because you know the magnitudes of all the eigenvalues are smaller. Right? So just knowing that the entries are positive, you get something that's way stronger than you get in general. This is where the utility really comes from for our, web search example. How do I know? Well, the theorem, I guess the theorem just says if you don't give me an A that's positive, then you're not promised anything. So webs aren't because there's zeros, right? So we'll have to deal with that. But strictly positive gets you close. Okay. Good. Good. So this is the theorem. Okay. And I've set it up to actually do this theorem, which is probably more pure math than you would like. So maybe we'll do it somewhat quickly. Okay. So this feels like a proof out of math class and basically is, so I apologize. So at least the proof I had in mind looks like this. Should I skip this? Well, let me maybe sketch it or something, okay? I gather up the set L, which is all sets of values lambda, such that ax is greater than or equal to lambda x for some distribution x. Okay? That seems like a weird way to start a proof, although maybe this style of proof you'll see often if you took, certain math classes. And we're going to try to argue is that the supremum of this set of lambdas will give you that top eigenvalue you're looking for. Okay? But then you have to show that L is closed, bounded, and these kinds of things so you can, apply Bose-Onnes stress and stuff like that. So, okay, so I guess we'll do it kind of quickly. Okay, the first claim is that L is non-empty. How can I guarantee there's at least one value lambda I can throw in there? Okay, get but we're not actually guaranteed that there's real valued eigenvectors. So this is really only focusing on x's that are distributions. Yeah. Yes, coordinate-wise. Yeah. Yeah. Yeah, smallest entry in A is probably good enough. So you can just pick a test vector, right? Like pick x to be 1s over n. And then ax is equal to a1s, I guess, divided by n. So just choose lambda to be, I guess, the smallest row sum, and you'll be okay. Okay. So that's fine. Here's another one, trying to show that L is bounded. How can we get an upper bound on any value in L? So 0 is a lower bound because all the values are greater than 0, but an upper bound? Sorry? Yeah, you can use the total sum. So for example, you know, if, maybe I've already written something here. Yeah, so if you have some value lambda in your set, which means there's some vector x that's sort of its witness, um, then you know that lambda, well, you could that's the same as summing up one's lambda x, right? Because x is a distribution, and this thing is at most one's ax, right? And all you know about x is as a distribution and everything in A is positive. So we can replace x with all ones. That's summing up all the coordinates. That'll give you some upper bound. Okay, so it's bounded. Uh, okay, here's the one that is probably really going to make your eyes roll, as opposed to eye rolls. Like eyes roll and eye rolls. I don't know. Okay, so L is closed. This is a little bit a technical thing. It means that if you take any sequence of points lambda and L and it's converging to some other point, that other point will also be in L. Okay, so that's not always the case, right? If I'm looking at all the points Euclidean distance strictly less than 1, I can gradually approach the border and converge to a point on the border, but the point on the border is not strictly less than 1, right? So what you want to do is you want to set something up. Did not do a good job there. Something like this. Suppose you have a bunch of points in your set that's converging to a point. You want to show that point is in this set L in a few minutes. Okay? So for each of the lambdas, you can find some certificate xi, right? AXI is greater than or equal to lambda xi. And what do I know about the sequence of xi's? Does it converge to a point? It doesn't necessarily converge to a point, but you can say something else. A subsequence will converge to a point. What's the name of this? Yeah, I know. I was so excited when like I got to use Bolzano-Weierstrass outside the context of a a classroom. Anyway, so Bolzano-Weierstrass guarantees there's always some subsequence of the simplex of the x's that will converge, right? If you remember the proof, it's like, oh, you're in a compact space, split it in half, and then at least one of the two halves will have an infinite number of points, split it in half, and the area goes down. Yeah. Yes. Yes. Oh, that's true. That's true. Okay, that's fine. I think also if I had replaced this as greater than or equals 0 inside L, it wouldn't be a big deal because we already found the point that's greater than 0. Yeah. Okay, good. And now you just can use continuity of linear functions. Okay, so we want to show, okay, so let's see. Uh, AX bar is a limit in J of AXIJ or something like this, right? And each of these are bigger than lambda J, XJ, right? And that's going to take you to lambda bar, X bar. Okay. So that'll give you a certificate for lambda bar. So it's also all of these things. And in the interest of time, let me just read off what we do next. So, okay, is this interesting? Good question. Okay, so you're going to choose lambda 1 is equal to the supremum in L, And because of all this non-empty, bounded, closed, in particular from above stuff, it's also going to be in L. Okay? So that's going to imply some x1 that's in the simplex such that ax1 is greater than or equal to lambda x1. Okay? So, yeah. See, I'm going to skip most of this. Okay, so from here, you want to show, so we do more work, and then you can argue that you must have ax1 is equal to lambda x1. Okay, I am now skipping steps. Let's see if I can quickly summarize why. No, it's just analytical. These are all like delta epsilon style proofs. Um, yeah. Okay, I'm going to skip most of the rest. What I want to do is I want to get to this point that was brought up in a question. Okay? Because this is a little bit fun and a little bit more easy to guess. So all I've really shown you from the first theorem is how you would get the lambda one, and then you have to verify the properties left, but it's not much fun and not much time. So let me do the next one. So let's let R be the random walk of a strongly connected graph. It does not mean that all the entries are positive. Okay? So we want to try to reduce to the all positive case as if it was like a full graph, with various weights. Oh, okay. Yeah, so that's the answer. So if it's strongly connected, that means that to go from point A to point B, there's some path that has most n minus one edges, either one or two or three or four or five or something like this, right? Now, if I just raise R to the nth power, okay, then that's only going to tell me where I can get to in exactly n steps. It's not quite what you want, right? So in other words, R to the n minus one may also have zeros. So how do I actually get something with no zeros? Sorry? That seems complicated. What's simpler? So it's strictly a combinatorial question, right? The problem is I'm trying to get some kind of like auxiliary graph or something where random walk makes sense. Yeah, so what about in terms of this whole like steps in the graph, right? The basic issue is that you can get to everyone in at most n minus one steps, but not necessarily in exactly n minus one. I'm trying to fill in all the edges, right? Add what? Yeah, you can add self edges and simulate the random walk, or choose a random number between 1 and n minus 1, and then choose how many steps, right? Okay, I might choose 2 steps, I might choose 3 steps, I might choose 4 steps. So that's summing up r squared, r cubed, r fourth, r5 to n minus 1. You might also want to include 0 steps I, okay? And just take the average, okay? And the eigenvectors for those r's are going to map to the eigenvectors and eigenvalues for this, and then you do the mapping back and forth. But the cute first step is instead of looking directly at the random walk of the original graph, look at it where we first choose the number of steps randomly, and then simulate the random walk for that many steps, and look at the resulting probability vector, right? So, yeah. Then you can get to anyone in one step because you can do up to n steps, and then that vector will give you the eigenvalues. Okay, and then you can do some math to verify these claims, but that's at least the interesting part of the idea. Okay, so I'll end it there. The real point is that the Perron-Frobenius theorem is why this vector exists. That's not at all true in real matrices. It's subtle to prove. I only showed half of the subtlety, but that's okay. And so we should be grateful for that. Okay, so next time we'll do other super exciting stuff. All right, thank you. But let me maybe point out the combinatorial part. So there's one theorem here that's very powerful, but it's maybe a better topic for a class really about linear algebra or a math class or something. You know, we did part of the proof just to get you a taste, but it would just be kind of more of this. Like, you know, it's not clear if I can come up with fun questions for us to, you know, guess things. It's not as combinatorial. It's just, okay, perturb this by epsilon, you reach a contradiction. I don't know if you've done these delta epsilon proofs before, but it would be a typical one. But maybe it is really important to point out, I think the real thing so the starting point is, I guess for me, a really big thing about my education was starting to use linear algebra for graph problems. I had taken linear algebra like many of you, or many of you will, and you know, you do the theorems, you do the thing, and then rank n and things like this. And then when I started using for graph problems, I started to think more about structure. Like there was more combinatorial meaning. I mean, there's a little bit in linear regression, but linear regression doesn't have nearly as much. Yeah, there's only so much you can do with like regression, right? It's kind of a simple problem. But like graphs, you can do a lot of stuff, and stuff that for whatever reason captures my imagination, and probably is correlated with you guys too, because we're in computer science and you're still here nearly 2/3 through the class. Uh, so, so for example, linear algebra first tells you there's eigenvectors. Okay, that's interesting. But then here's maybe an even stronger theorem, which gets into like, oh, just knowing that all the entries are strictly positive tells you much more than it just has an eigenvector. Tells you that the eigenvalue is real. The eigenvector is real and positive, right? Normally, the only problem is the complex eigenvalue, and I don't know how to ever interpret that. And it's non-negative. All other eigenvalues have strictly smaller magnitude. No other eigenvalues are non-negative. Actually, this just comes from orthogonality of eigenvectors and things like this. So this you can almost take as a given, as some kind of law, sort of like fundamental theorem of algebra. We did a little bit of the proof just to get you some taste. Maybe a more interesting point is trying to apply it to random walks of a graph. So random walk, everything is non-negative because you just have these probabilities for what are the odds for going from point A to point B. But if there's no edge, it's just a zero. Okay. Whereas we had this theorem that was all based on the entries all being strictly positive. Okay. It's like, okay, how can I find some kind of way to apply this very powerful Perron-Frobenius theorem to random walks, assuming the graph is connected, so you can go from here to anywhere else, strongly connected. Okay. And so the first suggestion was like, oh, okay, why don't I take my random walk matrix R and look at like R to the n minus 1? Because that would be like taking n minus 1 steps, right? And so that would be another stochastic matrix describing kind of a random walk, where a random walk in this new random walk is exactly taking n minus 1 steps in the original random walk, right? So all those entries will say, okay, if I'm here and I take n minus 1 random steps, what are the odds of being there? Okay, that will probably fill in a lot more, but you can still have zeros. Okay, and so because you might not be able to get someplace else in exactly n minus 1 steps, you can only get there in at most n minus 1. So what you can do instead is this random process. Well, I'm first going to choose a random number between 1 and n minus 1, or maybe between 0 and n minus 1 actually. So that will be k, and I'll take k steps. Yeah. So if I have like a bipartite graph, for example, you're just going back and forth, back and forth, back and forth. If n minus 1 is even, you always end up back here, right? So so the only difference is that, oh, we're saying is that we can get anywhere at most n minus 1. That's not the same as r to the n minus 1, which is exactly n minus 1 steps. So we can look at the exact matrix we'll look at something like Q, which is equal to, you know, the average of r to the 0, that's just the identity matrix. You just stay in the same spot, plus r to the 1, plus r to the 2, plus r to the n minus 1. Okay? So now since the graph is strongly connected, point A and point B, it can get there somehow. Maybe it's 10 steps. If it's 10 steps, then r to the 10 will give you a non-zero there. So this matrix Q is going to have strictly positive entries. We can apply all our things. Okay? And that'll give you some kind of vector x1 and lambda 1. It's not too hard to show that lambda 1 must be 1 for Q. But it's not hard to show that the eigenvectors of Q are going to correspond to the eigenvectors of R. Okay, because, for example, R to the 5 for this eigenvector x1 is going to give you lambda 1 to the 5 x1 and things like this. So the rest of the proof would just be kind of doing this due diligence of double checking this kind of thing. Double checking lambda 1 is going to be 1. And it'll just be verifying calculations. Okay. So the magical or really strong thing is this very strong Perron-Frobenius for strictly positive entries. That's why there exists stationary distributions and things like this. Okay. This is much stronger but more specific than like the spectral decomposition theorem or things like this, right? This is a very special situation. Yeah. Okay. So that's one example. And then today we'll give another example where we'll look at a different problem, different linear system, also based on graphs, and we're going to be able to get a lot of structure out of it. Okay.